Welcome back to you all. In the previous lecture, we have seen designing and working of DAC, digital to analog converter. We have seen the basic concept of conversion, the need of conversion. Now today we are going to talk about our first analog to digital converter. Okay, as I have already written, it is slow and because it's little complicated to understand also, and it has various steps. That is why it is little slow, but the accuracy is okay. In this case, accuracy is good. So let's begin with this is the circuit diagram, you can say, of this dual slope analog to digital converter. Okay, let's first we'll go through each component and we'll understand what is the purpose of those components, then we'll go with the working. Okay, the first is the switch. Okay, there are two voltages and this switch will toggle between two voltages. One is your V in and the other is your V reference voltage. As I have shown that V in is positive and V reference is negative. So one important point here is to note that these both should always be of opposite polarity. Okay, first thing. And the second is V reference will always be greater than V in. Okay, next is your op amp. See, this is the op amp and this op amp is configured as an integrator. Okay, and this will integrate the pulse what we are getting. So it is also known as ramp generator. Okay, next is your comparator. So the output of this comparator will be high only if the voltage provided at the inverting terminal is less than the voltage provided at non-inverting terminal, or in other words we can say if V voltage at V plus is greater than voltage at V minus, the output of comparator will be high. Okay, next is your clock. We will be providing this clock at one input of this NAND gate, and the output of NAND gate is connected to the clock of counter. Okay, now this is the counter and depending on the number of bits it will up count, and the maximum count will be 2 raised power n minus 1. As we all are aware that if I am designing mod or let's say 4-bit counter, so what is the maximum count? The maximum count will be 2 raised power 4 minus 1, that is 15. Similarly here also if I am using n bit of counter, so it will up count until 2 raised power n minus 1 and total number of count will be 2 raised power n. Okay, and from here the output of this analog to digital converter will be taken. This is the output of a resistor. Okay, so that is how we have explained the circuit diagram of analog to digital converter, that is dual slope analog to digital converter. Now let's go with the working of that. Okay, so here let's say I have taken any input voltage V in. So what is the scenario here? If I have already told you that it is an integrator, this circuit, this is an integrator. Since the input is connected to the inverting terminal, the output will be negative. See, because it is an op amp, and in op amp if you are connecting input to the inverting terminal, the output will be negative obviously, and that too will be according to the applied voltage. If I am applying or in other words you can say that will be proportional to the input. Okay, so yeah, V naught is some negative voltage and proportional to Vi. Okay, next what will happen? See, here I have plotted this graph also. So as long as input voltage is applied, your output will become negative, and here I have represented by V naught. Okay, so this graph is representing the output, and as I have told you that it is negative, that is why the axis is in the negative direction. Okay, what next? Now the comparator, the voltage at the terminal is negative. See, the voltage available at the inverting terminal is negative and the positive terminal is connected with ground. So obviously that the condition what we have discussed earlier, that V plus should be greater than V minus, is satisfied. So the output of comparator will be 1, and if this is 1, in that case what will happen? See, one input of this NAND gate is connected with 1, so the output of this NAND gate will entirely depend on the other input, and if other input is clock, so that clock will ultimately appear at the output of AND gate. Okay, so in conclusion we can say that your counter has got a clock. Okay, now counter will start up counting. Okay, and how long it will count? it will count until its maximum value. Okay, so once maximum value is reached, what will happen? This TC signal will be enabled, since clock required by the counter to reach its maximum value is fixed. Hence the time for charging the capacitor is also fixed. We'll explain this little further in the last discussion also. So as of now, we can conclude that with the help of that clock, your counter will start counting, and as long as if let's say if this is a counter and it is having mod 16, let's for the sake of discussion only. So if it is having mod 16, so it will take 16 clock pulses to count. So this time period is fixed now, and once it is reached to its maximum count, then what will happen? Hence let's see what will happen at that time. This TC will be enabled, and once the TC is enabled, then the control, now here this control block will come in through the picture, and this control signal or this control will enable the clear. Okay, this control will enable the clear, and the output of counter will, or the counter will reset. The counter will reset, and at the same time this control signal will generate a pulse, and that will change the input also. See, now what will happen? This switch will be connected to V reference now. Okay, so as of now, what we have seen, that with the help of or the applied voltage, your integrator has generated a negative signal, negative voltage, and according to that negative voltage, the output of NAND gate has changed, and NAND at the input of at the clock of this counter, we have got a clock pulse, and that has resulted in counting. And once the counter has reached to its maximum count, this TC will enable, and the counter will reset. Counter will be reset to 0, and at the same time a control signal will be generated that will change the switch, and now the switch is connected to V reference. Okay, now let's see what will happen next. Now here, as you can see, that this V switch is connected to V reference, and that is negative. Okay, so now as I have already discussed, that V reference is always greater than V input. So obviously V naught is less negative than V reference, that is polarity is reverse. Now that will lead to the discharging of the capacitor. Okay, now your capacitor will start discharging, and hence what will happen? The voltage at the inverting terminal of this comparator will keep on decreasing, but still the condition what we have taken in the beginning is satisfied. Okay, so the output of comparator will be 1, will still be 1, and rest of the things will repeat itself, and AND gate will pass the clock and counter will start counting. But how long it will count? Until V naught is not becoming 0. Okay, see here V naught has become 0. So at this point, or after T1, your counter will stop counting. Okay, so when V naught will become 0, condition V plus should be greater than V minus won't be satisfied any further. Output of comparator, and hence AND gate will be 0, and the counter will stop counting. At this time, what will happen? Control circuit will enable the resistor, and the count of the counter will be stored inside the resistor, and hence the conversion is completed. See what will happen here? From the comparator, a control signal is generated. That control signal will enable the resistor, and whatever count of the counter would have been at that time, that will be stored in the resistor. Okay, that is how this process, or this dual slope analog to digital converter work. There is one more important thing I would like to emphasize on that. Let's say I have taken a voltage V2 which is greater than V1. In that case, what will happen? Since the charging time, that T is fixed. Okay, so what will happen in that case? The capacitor will charge to a higher value, because the applied voltage is high, but the time to get charge is constant. So this capacitor will be charged for a higher value. Okay, if the capacitor is charged for a higher value, and so mean here one more important thing, that the slope is not fixed in this case, but the time is fixed. Okay, here we have observed that we have fixed count with variable slope. What would be the next? See, now we have got the output of this you can say comparator is not comparator, sorry, this integrator is high. So if the output of this integrator is high, then that will take longer time to discharge also. See, here the count is different, but the slope will be constant, because the discharging rate of discharging is constant. So the time taken by the capacitor to discharge will obviously be larger or greater. So if what I mean to say, that if I am taking small values of input, at that time the capacitor will charge to smaller values, and the time required to discharge the capacitor will be smaller. But if I am taking larger values, in that case what will happen, your capacitor will charge for higher values, and the time taken by the capacitor to discharge will be comparatively high. Okay, so if the time taken by the capacitor to discharge is high, then accordingly your counter will count. Okay, so for, let's say, for T1 your counter has counted till 011, and for T2 it has to count for a larger value, so it may count to 0111. Okay, 7. So this is the concluding remark. Here I have written in the discussion. We may conclude that if Vin is large, then the capacitor will charge for higher values, and hence the discharging time will also be high, and hence the count of counter will also be high. Okay, so I hope that you have understood this. This 20 volt in Vin, that is written by mistake, this 20 volt. Okay, that's all for the day. Thank you.